I use the same number. All right. Rope hanging from a building. Let's find the work necessary to pull the rope up. So we don't need Hooke's law, do we? But we do need this. We do need this. So in this problem, everyone, let's find the work necessary. To lift the rope. And then when this is a heavy rope, so I'm going to put the word heavy rope. I'm going to write heavy rope. Find the work necessary to lift a heavy rope that weighs 2 pounds per foot. And then I got to give you the length of this rope. It has length 100 feet. Find the work necessary to lift a heavy rope that weighs 2 pounds per foot and has a length 100 feet. And I'm going to say, I'm going to use the same wording I see here in the book, to the top of the building. And you and I can even discuss the building, because I don't want that to bug you. This is what we'll work out. Find the work necessary to lift a heavy rope that weighs 2 pounds per foot, has length 100 feet to the top of the building. Alright, we're talking about like heavy ropes. Some problems have heavy cables. Right, you think of those heavy hoses used by the firemen, that kind of stuff. Really heavy. Okay?
Are we assuming that the building is not the building?
Great question. So in this building height, sometimes they include it in the problem. Like the building's 300 feet in height and stuff. That's not going to affect any of our work. Alright? But they should give you some indication that in this problem, we should point out this, that rope, it wasn't like a 8-foot high building. So that the rope wasn't what? Lying on the ground? So let me just pick the height of a building that's higher than 100 feet. How about a 500-foot tall building? Does that work? So in the building we're talking about, if you want to include it right now, it's a building that's 500 feet in height. And we're going to lift this rope to the top of the building. But you're not going to put that 500 anywhere in your mathematics, true? That's just indicating that no part of this rope was lying on the what? The ground, as we were pulling this up. This rope's just dangling off the what? The roof. Here it is. Here's that rope. There it is. And how long is this rope? It's really long, but it's 100 feet in length. So the first thing we have to do, or we're about to do this, is we got to really talk about how the force is applied at different spots. See, the force applied here is different than the force applied here. You all agree? And that's what's going on. That's why we need calculus. The force applied right there is different than the force applied right there. So I'm just going to take a tiny slice somewhere in this rope, and then we're going to talk about how we're going to sum up an infinite amount of these. All right? So how about right here? This tiny slice right here. And when I just took a tiny slice, cool. How much of that? Oh, that's just like a change in X right there. We also need to scale this. So do you want to scale X, if I use the letter X equals 0, this would be what, X equal to 100? Or I could use X equals 0 here, and how far down would this be? X equal to 100. It's really up to you. To start this problem, I'll tell you what I'm going to do. I'm going to scale it as X equals 0, if you don't mind. And then I'll scale this, so that means this value right here would be X equal to 100. And this is my scale. And we could talk more about that later, like if you like, is one better than the other? But I could have scaled this as x equal to 0 here, 0 feet, and this would be what? 100 feet. If you're curious why I put x equals 0 at the top, just me, because we're trying to lift this thing where? Yeah, to the top. That's why I did that. I think it would be easier when it comes to representing distance x. All right? So now, right here, there's that slice. And what's work equal to? I'm going to write it down. Work equals force times what? Distance. I'm going to write that down. Work equals force times distance. But we know it right there, that's that tiny, tiny little slice I took, right? Eventually we're going to have to what? Sum all these up. Cool, but I'm going to start with that little slice. I'm going to write down work equals force times distance. Let's talk about the force acting on that little slice. It deals with the weight of the rope. What's the weight of this rope? So I'm going to write 2 pounds per what? Foot. Sound good? 2 pounds per foot acting on that little slice. Now, how much of that slice did I take? I took just what? Infinitely small. So I'm going to call it change in x. Foot. Everyone see that? There's my force. Show me the word distance. Eventually, we're going to set this up with an interval. 2 pounds per foot acting on how much feet of that rope? Just a tiny, tiny what? Change in x. Cool. Now, what's the distance down this was? Well, everyone, because I scaled this as x equal to 0 here, can I call this distance x? I want to make sure one agrees with me. Everyone? Can I call this distance x coming down here? I love it. So I'm going to call this distance x from the top. Cool. Now, I'll just draw an arrow. Elongated S. Integral means I can sum all these what? All these little slices all the way down. That's all I'll do. So I'm going to sum all these. It looks like I got a 2. What letter here? X. Now, do you know what the change of x turns into in an integral symbol? Can you all see? What's change of x really become? Dx. All right? I'm serious. Just think about it like that. Like that change in x is going to be represented by the what? The dx. This is why I wrote it like this earlier today. I wanted you to see that sometimes you look and you're like, I'm talking about a very, very infinitely small, infinitesimal slice from there with change in x. And what happened to these terms, feet and feet? They just what? Cross out. So I now have 2. Change in x is just the what? The dx. But you still have this what? This x was for the distance down here. So when I do want to point out, you go, where's he getting x from? X was the distance that this slice that I took from the top. That was the distance from the top. 2x, dx, not a bad problem, huh? What's the limits though? How much was that rope? From 0 to what? Yeah. And the answer will be in what units? Because this is the US customer units. Foot pounds, right? You got the pounds and you got the foot. Alright, well let's see, what do we get for answer? Let's integral 2x.
2x squared.
Boom, and then 0 to 100? What's 100 squared? 1, 0, 0, 0, 0, and foot what? Yeah, I would like to show you what we have to do if you scale it the other way, okay? So if someone wants to scale it the other way, I want to present that to you as well. But you heard me. What was my preference? I scaled it as x equal to 0 from the top because where were we lifting this rope? To the top, right? It wasn't like we were sitting at the bottom pulling this thing or something. And we just found the work necessary to pull it to the top. Now I would like to show you something. I don't care if you put this off to the side. I don't care if you don't even copy this. How could I set up this problem? I'd get the same answer, but if I scaled this thing. Okay? Just if someone's curious. So, what if, I'll put it over here. I don't care if nobody copies this. What if I did this? And I'm going to put it back like this. What if I did this? Your x equal to 100, and your x equal to 0. Okay. Well, it looks like this will be the same, right? This will be the same, right? What's the distance though? Well, what would I call the distance? Let's pretend this number right here was at like, gosh, 100, let's say this was at 60. How far down is 60 from 100? Do the math. What would be 100 minus 60? 40 feet. So we need to make sure that when we plugged in the value 60, what comes out? Distance 40. Does anybody know a math formula I can put for distance if I scale it this way? It's not so simple as x, but it's pretty close to it. You got it. I'm going to put it right here. Just in case someone in here wants to approach the problem this way. Watch how this works. With the 60, what's 100 minus 60? How far would that distance be? 40. Or try, look, what if this was 70? What's 100 minus 70? Distance 30. And way down here, this would be a what? 10. What's 100 minus 10? Oh, you got to lift that rope 90 feet. Do you follow me? So if you want to do the problem that way, of course you can. But I scaled it this way originally because I felt, oh, that would be easy to work. Both of these give the same answer. I know they look different, but you still get the same mathematical answer.
I don't understand why you have to subtract it from 100 because since you're just having x represent any distance, isn't it arbitrary where like
you can. Like you're saying, this is why you're arguing for this. You're saying you could solve the problem this way and you're actually right. But I wanted to point out that some students approach the problem this way. Look, it looks different from that, but this will give the same exact answer, the same amount of work. Because someone might have looked at their picture this way, right? Because we really have to scale it to look at it. And even like, we won't do every work problem today, but tomorrow we might have like some other different type of design, not a rope, but maybe a pool. And like, we'll decide which way you want to scale it. Like, where's 0 feet deep, or 5 feet deep, or 7 feet deep? Which way are you going to twist that scale? So it's a really good point. You're arguing for this, and you're right. You're saying it doesn't matter. But I did want to point out, if someone looked at the problem this way, and they're saying, okay, when you substitute a 60, it's a distance of how far? 40. Then they're saying, okay, my distance from the top, here, write this. Distance from top was, and when you plug in the values, because they're summing up an infinite amount of these, 100 minus 60 will give you the 40s. But I like what you said. You're arguing for this. That's why I started your way. I actually agree with you. It's like, this is easier. There's no need to do that, right? Hey, we got to extend this problem. So now everyone, right at the bottom of this, I'm going to add this 700-pound dude, okay? Now, if you're like, wait, he might move around, that might affect the force. All right, just pretend he's what, not breathing or something. The dude. We're putting him at the bottom. So I'm going to change the question is, I want you to find the work necessary to lift the heavy rope that weighs 2 pounds per foot and has length 100 feet to the top building. And I also want the total work with that combined with lifting the what? The dude. Okay? I think the bulk use like a lump of coal or something. Right? You'll notice in the practice problems, they just put something like 500 pounds of equipment or something. I just used a 700-pound what? Dude. Attached at the end of this what? Rope. And hey, I'm going to use this method. Okay? Where we already got the work necessary to pull the rope. Well, let's put a plus. What else do I got to add? I need the work to lift the what? The dude. Well, good news. Everyone, check this out. I got to lift him how far? 100 feet. Look what I put here. How much does he weigh? 700 pounds. You bet everyone, look, I didn't put an X. Isn't that constant? In fact, some of you might even write this integral symbol. Can't you just do what? Force times distance? What's 100 times 700? Just take that and add it to the last answer. Isn't that what we can do? Do you all agree? I want to point this out. It wasn't like the rope where the force acting here was different than the force acting here. Because this was 2 pounds per foot. That's how much this rope weighed. We're just going to lift this heavy dude up also as well. So we're just going to add this, and everyone, that's just a 700 without an X. So, what's the integral of 700? And you see what's happening here, everyone? You're just going 700 times 100, which is, how many zeros there? 1, 2, 3, 4. All right, what's the final answer now? So we got 10,000 foot-pounds plus 70,000 foot-pounds equals 80,000 foot-pounds. Question, go ahead.
I was gonna ask, what is the force on the rope carrying 700-pound dude bearing?
Great question. Since we already took care of that rope, we're just thinking that person, we're just thinking it's just some constant force the whole way out. And it's a great question. And I want to, if you could put this in your notes, when you do a practice problem, there's a problem with the cable. And when it's number 15, when you practice number 15, can I just read it to you? A cable that weighs, okay, they use 2 pounds per foot too, but a cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft 500 feet deep. Do you care about that 500 feet in your problem? No, but you'll find you need to do the work to lift that actual cable, do that separately, and then add it to the work to lift that coal. But with that coal, it's just going to be like this. You can just think of it as, because what got added to this 10,000? I didn't have to write the integral symbol, did I? The force was what? 700 pounds, and what was the distance? And that was constant. That was constant. Different because the cable, what's going on with that rope? Well, it's a very heavy rope, and it was 2 pounds per foot. And so when it's per foot, you're like, okay, it's changing at different depths. Awesome.
Can we just put it in the same integral? Like 2x plus 7?
I love it. Let me show you what he just suggested. You ready? See how I wrote it here? He goes, well then why don't you do this? He goes, do one angle, 0 to 100, 2x plus 700. Do I put an x here? No. And it's kind of right? Kind of very good. Don't you agree? That's actually a great idea.
If you pull the 700 out and make it constant.
But the 2, huh? You could factor out a 2, but then this would become what, 350? So you might want to just leave it there, if that bugs someone. So I like the idea of taking something out, but because it's a summate, it's a sum here, we can only factor out a what, a 2? Cool. So either do this, or do what? Or do this, dx plus up. Just watch this carefully. 700, any x there? For the dude or the coal? No, just 700. And this just becomes what? That's that constant force times distance that you get out of that. Hey, cool. Hey, what we're going to do is, we'll keep doing work tomorrow, but we're going to do one more of these. All right, we're going to do one more. This time, everyone, it's going to be a cylindrical swimming pool. All right? That means it's got water in there, right? So they got to give us some numbers. So let me just put the word water down. Have we had any problems with water yet?
Yeah. So
can we just write down water? If everything's in U.S. customary units, they do give you the weight of water. Water weighs 62.5 pounds per cubic foot. If you want to memorize that, you can. Water weighs 62.5, let me get that decimal there, 0.5 pounds per cubic foot. So let's just talk about the units right away, if we're using U.S. customary units. Aren't we going to have to use that in our mathematics because of the weight of water? We're talking about force times distance, right? So if you got water involved, we haven't had it yet, use that. And yes, everyone, don't laugh, I've had students, we're talking about ropes before, they go, don't I need the 62.5? And I know, I see some smiles, it's like, they're just, the section's probably overwhelming to them, right? But we only need that 62.5 if you're dealing with what? Something with water, like you're pumping water out of some pool or something like that. That's the weight of water, but we didn't need it with that rope or cable, or did we need it with the spring? No. Now, what about metric system? All right, what they're going to do in the book, and I'll put it down over here, I'll put down a number, is in the metric system, they will give you the density of water. So let me just start with that. Density of water, 1,000 kilograms per cubic meter. All right, so I'm gonna start there, and then I'll put a number down here eventually. This is because half the problems in section 6.4, we know this, are dealing with the, metric system. They call it the SI metric system, Standard International. International standard, right? There's 3 countries that don't use the metric system. You got what? US, anybody know the other 2?
UK and New Zealand.
Burma and, I'm blanking on the other one, Liberia. Liberia and Burma are the 2. I know Liberia, I have to check again. But what do all the other countries use? They have metric. The Standard International Metric System. Well, here's a density of water, 1,000 kilograms per cubic meter. Now, let's talk about mass. Well, mass will equal density times volume. All right, I'll put this down. This is if we're dealing with water, everyone. If we're dealing with water, they give you this number. All right. Well, you got the density, which is what? 1,000 kilograms per cubic meter. And you agree, whatever we have in terms of volume, if it's water in a swimming pool, isn't that going to be in cubic meters? Because it's 3-dimensional, right? It's volume. So I'm just going to be an m cubed here, and let these m cubes cancel out. So right now, we got it at 1,000 what? Kilograms. But now, one more thing, gravity is still in play. So you got force equal to m times g, mass times gravity. So you got the 1,000 kilograms, and this g is gravity. What's gravity in the metric system? 9.8 meters per second squared. So I'm going to put that down. 9.8 meters per second squared. And this is the number that you want altogether when you're dealing with the work problem with water if you're in the metric system. What's 1,000 times 9.8?
9,100.
I'll write it really big. 9,800 units look like what? Kilograms dot m over what?
Second square.
S squared. And I want to tell you there's a unit for that. That's equivalent to the kg dot m over s squared. And it's a big old N. What's big N stand for? Newtons. So, hey, to keep it simple, I got a lot of writing on this board right here. I want to keep this simple for you. You say if you're dealing with a problem with water, and you're using US customer units, you'll recognize it right away when you read the problem. Then what's the number you're going to have to include in your answer? 62.5. Jessica, we could just put it right at the front of the integral, okay? If you're in the metric system, what's the important number going to need? This what? 9,800. And you would use that. So I'm just going to put 9,800. Big old N, everyone. That's if you're in what? Metric. These are the 2 numbers. Don't let it bug you, because you'll see so many problems. I'm just going to hold this up. We're going to do one problem together. We'll just set up the integral. But you see all these little tanks they got? They're all filled with water. That one, that one, that one, and that one, they're all filled with water, and you can tell they're different shapes, aren't they? One looks like a sphere, one looks like a triangular trough. So we got to look at these carefully, right? Well, the one we're going to do is like number 20. Actually, it is. Yeah, number 20. So can I erase this? This is just so you know how that number comes about. And when a circular swimming pool has a diameter of 24 feet. Diameter, 24 feet. There it is. This is number 20, and when it's in from section 6.4. Okay. Sides are 5 feet high. I'm going to keep reading. I'll put that 5 feet high down. I'm going to write the 5 in the picture. The water, everyone, is not filled to the top. You know, with some of the swimming pools even today, you go out there and you want to go in. Isn't it usually a little bit lower than the top? So, and this is what they said. They said the depth of the water is 4 feet. How much work is required to pump all the water over the side, out over the side? So this is important to me. which way are we pumping this water? Because I saw a gentleman in the Navy, and I think they have pumps, a lot of them pump downward. They're in submarines and stuff, a lot of things pump stuff this way. Well, this water's getting pumped which way? Up out of the top. So just me, when it comes to my scaling decision, I'm gonna scale this thing, I'm deciding, you know what, since I'm pumping the water this way, I'm gonna put x equal to 0 right there. So what would x equal to right here? 5. You wanna put some dashes in the middle here? 1 and what? 2 and 3 and 4. I need to scale this thing, right? Remember, you could scale it from the top, x equals 0 to x equals 5, or vice versa. I just thought this is the way I'll scale it. Why are you doing that? Just think it's easier because I'm pumping it out of the top. When I have to come up with that formula for distance, I can just call it distance x, right? Okay. Now, how much is filled? They said 4 feet in depth. So let's, at least on this board or in your notes, fill this up with water. Because this is important to us. When we do our integral, everyone, I'll be honest, looking at this image, we are not going to do integral 0 to 5. Because the water is not filled up from 0 to 5. We are not going to set up that integral from 0 to 5. No way. Because the water wasn't filled all the way to the top, right? How far was that integral filled? Or I mean, the integral, how far was that swimming pool filled? So does anybody already know, when I set this up eventually for my integral, the limits? Do you already know, just looking at it? What would be the limits of integration? 1 to 1. I just want to point that out from that image. That's your limits of integration. When I find my work, in the end, I'm going to have this. Okay? Just so you're not confused. And sure enough, what if this was filled to the top? What would I have used? 0 to 5. Very good. Now the hard part is this chunk, which I don't think you're going to find hard. I'm going to come up with this what? Remember this force times what? Distance, but it changes at different places in that swimming pool, right? The force acting here is different than the force acting here. So before I write this, I'll come back to this. This is what we have to do. Let's take out one slice. So right there, I'm going to take a slice right there. One infinitely, in terms of height, infinitely high slice of water. And I'm going to pull it out. What would it look like? Because when this was a circular swimming pool, that slice would look like what? A circle. But I'm going to give it a very, 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 very small height. Because this does have volume, doesn't it? What's the volume of a cookie like that? Pi r squared times the what? The height. All right, so for this volume right here, this is my force. I'm going to have to take the volume of the slice, and I do have to multiply the number for water. What was it? Are we in feet or are we in like the metric system? U.S. customer units, right? Don't worry, tomorrow we'll get some problems in the metric system. This was in feet, so I'm going to do this times what? 62.5 pounds per cubic foot. Okay. That's common. This is the force. All right. But what's the volume of the slice? I need a formula for the volume of like a cylindrical tank. That's pi r squared times what? Height. Let me say that again. Do you all agree? What is the volume of a cylinder? What is the volume? Because that's a cylinder, isn't it? It looks like a little cookie. Start thinking that height's just going to be our change in x, right? But the volume of this little slice of water is pi radius squared times the height. Now, what's the radius of that thing? You all should know it looking at the picture. The radius is always what with every slice in that picture?
Well,
they said the diameter was 24 feet. That means diameter from there to there, all the way across. What's the radius? 12 feet. Does everyone see how I got that? Now, pi radius squared, this is volume of this one slice. Of this one slice, what's the height? Changing it. That's my little height. That little right here, you can just draw an arrow and go, that height has a change in x. So I take all this right here, and I'll multiply it to the what? 62.5 pounds per cubic foot. All right? And you bet everyone, 12 feet times a change in x feet, all the feet will go away and this will just be in pounds. Cool. So all this will just turn into pi 12 squared, 62.5. What's the change in x become in the integral again?
dx.
dx. Say it again. Change in x, what will that actually turn into? dx. Cool. So I didn't want you to think that turns into x before. Now before I mess this up, I'm going to put an integral and put all this stuff, I'm going to put that as dx. Go from 1 to 5, but one more thing. This was just the force acting on this. What's the distance down the slice was? I mean, here's that slice I picked. Don't I have to talk about how far down it was? The distance? So let me go right next to it. That was a force. What was the distance from the top that slice was?
X.
X. Someone see that? And now here I go. Here's a smiley face. I'm going to set up this problem. It's 62.5. What else could I pull out in front? Pi, integral from 1 to 5. What else do we got? There's a 12 squared. Should I put that in front too? Heck yeah. Now let's put the 62.5. Let's put the 12 squared. We can put any constant out in front. The pi, integral from 1 to 5. But this distance is right there. Oops, that's a 5. And what's this change in x become? I'm going to draw an arrow. This becomes a, that's your dx. I just want to be careful, make sure that no one accidentally forgot to think about the distance down that slice was. See how we did this? I did this with cylindrical shells. I said, let's look at one shell and think how you sum them all up. That's what we're doing. We looked at the force acting on that one slice. And now we're like, this would give me the work necessary. Right here. Hey, just to finish this out, I don't know what 62.5 times 12 squared is, times a pi, but I knew the integral of x is just what?
X squared.
X squared over 2. You just got to go from 1 to 5. So this would be my answer, 62.5 times 12 squared times a pi times 25 over 2 minus 1 over 2, whatever that comes out to be. Oh, and what's the units?
Pounds.
Foot, pounds. Do you want to leave this in terms of pi? I'll do it right now on my calculator. What's 25 over 2 minus 1 over 2? 12. So what's a 12 times a 12 times a 12? I'm like, what's this? What's 12 cubed, right? Now I'll do all this math. 12 cubed times 62.5. Here's my final answer. My final number is 108,000 foot-pounds with a pi though. I kept the pi in it. I didn't multiply the pi. I'll put pi foot-pounds. Anyone care with that? Y'all get the same? Nice. Hey, we're not done with work, are we? Tomorrow, let's look at, what if it looks like that? That was a nice circle, you know. Did the radius change? Sometimes the radius may change. Let's look at scenarios like that. You know, and we'll wrap up work. Great section, but you do have to look at everything separately. Have a great day. And I know I can answer your question.